Application of roots in physical contexts. Welcome, everyone. To begin today's lesson, let's take a moment to reflect on what we have covered so far. In our previous lessons, we focused primarily on the algebraic mechanics, the step-by-step process of finding the roots of a quadratic equation using methods like factoring or the quadratic formula. As you know, when we look at a quadratic equation, specifically x squared plus bx plus c equals 0, the mathematics tells us that we can yield two distinct real roots. From a purely symbolic standpoint, both of these numbers are perfectly valid answers to the equation. However, today we are shifting our focus. When we take these equations and apply them to solve real-world problems, things like calculating the dimensions of a room, determining the speed of a moving vehicle, or even finding the age of a person, we are moving from the realm of pure mathematics into applied mathematics. This is a crucial distinction. The core principle you must keep in mind as we move through this topic is this: mathematical solutions are not always physically possible. As we will see in the next slide, we need to learn how to distinguish between a mathematically correct number and a physically valid measurement. Understanding physical validity. Now that we've established that there is a difference between pure algebra and applied mathematics, let's look at slide 2 to understand exactly how we determine physical validity. When we take a word problem and derive a quadratic equation from it, the variable $x is no longer just an abstract symbol. It usually represents a specific physical quantity, like a distance or a duration. Because of this, we have to respect the real-world constraints that these quantities carry. Think about it this way. In the real world, certain measurements simply cannot be negative. For instance, dimensions like length, width, or height must always be positive values. Similarly, when we look at time elapsed in most standard physics problems, we can't have a negative amount of time passing. The same applies to age. A person's age cannot be a negative value. Even when dealing with motion, while velocity can be negative to show direction, speed is a scalar quantity, meaning it must be non-negative. So, here is the most important takeaway for your exams. If you solve your quadratic equation and your algebraic results give you one positive root and one negative root, you cannot simply list both. That negative root is considered extraneous or invalid because it contradicts physical reality. In these cases, you must explicitly discard the negative value and only proceed with the positive one. Step-by-step approach to solving physical problems. Now that we understand the concept of physical validity and why some mathematical answers simply cannot exist in the real world, let's look at a structured way to approach these problems. To ensure you are always accurate when applying quadratic equations to real-world contexts, I want you to follow a specific, systematic approach. First, we have step 1, model the problem. This is perhaps the most critical stage. You need to translate the English word problem into a mathematical equation. To do this effectively, you must define your variable, x, very clearly. For instance, instead of just saying x is the width, you should be specific, such as, let x be the width of the rectangle in meters. This keeps your units and your meaning clear from the very start. Once you have your equation set up, we move to step 2, solve the equation. At this stage, you are back in the realm of pure algebra. You will use your preferred algebraic techniques, such as the method of factorization or the quadratic formula, to find the possible values of x. Keep in mind, as we discussed in the previous slides, that this step will likely give you more than one value, which leads us directly into the evaluation process we will cover in the next slide. Step-by-step approach to solving physical problems, continued. Step 3 is to evaluate the roots. Once you have finished your calculations and obtained your possible values for x, don't stop there. You must carefully examine each root you've found. I want you to pause and ask yourself a critical question. Does this value actually make sense in the real world? This is where we bridge the gap between pure algebra and physical reality. Moving to step 4, you must discard invalid roots. As we discussed in the earlier slides, certain values simply cannot exist in a physical context. If one of your roots contradicts physical reality, for instance, if you get a negative value for a length or a negative value for time, you must explicitly state in your working that this root is rejected. It is mathematically a solution to the equation, but it is not a valid solution for the problem. Finally, in step 5, you will state the final answer. Take your remaining valid root and use it to provide the complete answer to the original question. And please, a very important reminder, always ensure you include the appropriate units, such as centimeters, meters, or kilometers per hour. A number without its unit is incomplete in applied mathematics. Now that we have covered how to model and solve the equation in the previous steps, let's move on to the final part of our systematic approach. In the next few slides, we are going to see this entire process in action with a practical, illustrative example. Illustrative example. Here, we are presented with a word problem. The length of a rectangular plot is 3 meters more than its width. We are also told that the area of this plot is 40 square meters. Our goal is to find the actual dimensions of this plot. To solve this, we will follow the systematic approach I mentioned in the previous slides. The very first step is to define our variables. We need to translate these words into mathematical terms. Let's let x represent the width of the plot in meters. Since the problem states the length is 3 meters more than the width, we can express the length as x plus 3 meters. This sets the foundation for us to build our equation in the next step. Now that we understand the theory behind distinguishing between mathematical roots and physical reality, let's put this into practice with an illustrative example. Illustrative example, continued. Now that we have clearly defined our variables in the previous step, letting x represent our width, we need to move on to the next crucial stage, formulating our equation. To do this, we look back at the information given in our word problem. We know that the area of a rectangle is calculated by multiplying its length by its width. Using the expressions we just established, we can set up our equation as x multiplied by the quantity x plus 3 equals 40. Now, let's expand this to get it into a standard quadratic form. When we distribute the x into the parentheses, we get x squared plus 3x equals 40. Finally, to prepare the equation for solving via factorization, which we will see in the next slide, we need to set the entire equation to 0. By subtracting 40 from both sides, we arrive at our final quadratic equation. X squared plus 3x minus 40 equals 0. Illustrative example, continued. Now that we have our quadratic equation, which is x squared plus 3x minus 40 equals 0, let's move on to the solving stage. We are going to use the method of factorization. To do this, we need to find two specific numbers. These two numbers must multiply together to give us negative 40, and when added together, they must result in our middle coefficient, which is positive 3. If you think about the factors of 40, you'll find that 8 and 5 are the perfect pair, specifically 8 and negative 5. Let's apply this to our equation by splitting that middle term. We rewrite x squared plus 3x minus 40 equals 0 as x to the power of 2 plus 8x minus 5x minus 40 equals 0. Next, we group the terms to find common factors. In the first two terms, x squared and 8x, we can factor out an x in the second two terms, negative 5x and negative 40, we can factor out a negative 5. This leaves us with x times the quantity x plus 8 minus 5 times the quantity x plus 8 equals 0. Notice that both parts of our equation now share the common binomial factor, x plus 8. By pulling that out, we arrive at our final factorized form. The quantity x minus 5 multiplied by the quantity x plus 8 equals 0. This brings us directly to our next slide, where we will solve for the individual values of x. Illustrative example, continued. Now that we have successfully factorized our quadratic equation into two binomial factors, we move to the next step, finding the actual roots. To do this, we apply the zero product property, which tells us that if the product of these two factors is 0, then at least one of the individual factors must be 0. First, we take the first factor, x minus 5, and set it equal to 0. Solving this simple linear equation, we find that x equals 5. Next, we take the second factor, x plus 8, and set it equal to 0. This gives us x equals -8. So, we have arrived at our two potential mathematical solutions, 5 and -8. Now, as we will see in the next slide, we cannot simply accept both of these values as our final answer. We must now evaluate them against the physical reality of our original problem. Illustrative example, continued. Now, this is the most critical part of the entire process, and it's where we transition from pure algebra back to the real world. We need to evaluate the physical validity of the roots we just found. Remember, our variable x represents the width of the rectangular plot. Now, looking at our two mathematical results, we have x equals 5 and x equals -8. In the context of geometry, a width cannot be a negative value. A plot of land cannot have a width of -8 meters. Therefore, we must conclude that the value of x equals -8 is physically impossible. And we officially discard it from our solution. We are left with only one mathematically and physically sound value to be worked with. Illustrative example, continued. Now that we have evaluated our roots and rejected the negative value, we can arrive at our final dimensions. Since we determined that the negative root was physically impossible, we are left with our valid width, which is x equals 5 meters. To find the length, we simply refer back to our original definition where the length was x plus 3. Substituting our valid value, we get 5 plus 3, which gives us 8 meters. Therefore, our final answer is that the dimensions of the rectangular plot are 8 meters by 5 meters. This completes our problem-solving process, moving from a word problem to a valid, real-world solution. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls that students often encounter when working on these types of problems. If you can avoid these 3 mistakes, you'll significantly improve your accuracy in exams. First, let's talk about accepting all roots. As we saw in our rectangular plot example just a moment ago, the algebra gave us 2 different answers, 5 and -8. A very common error is to simply list both of these as your final answer. Remember, while both are mathematically correct solutions to the equation, only one makes sense in the real world. You must always act as a filter, checking your mathematical results against physical reality to ensure your final answer is logical. Second, please be careful about ignoring units. In pure algebra, a number is just a number. But in applied mathematics, a number without a unit, such as meters, kilograms, or seconds, is actually an incomplete answer. If you find that the width is 5, but you don't specify 5 meters, you haven't fully solved the problem. Always ensure you attach the appropriate unit to your final, valid root. Finally, watch out for incorrect variable assignment. When you begin a problem, try to assign your variable, x, to a quantity in a way that keeps your equation as simple as possible. For instance, if you choose to let x represent the length instead of the width, just make sure you adjust your expressions accordingly and that your constraints still align with physical possibility. By keeping these points in mind, you'll be well prepared for our final summary of the key takeaways. Key takeaways. First, I want you to remember this fundamental distinction. A mathematical root is not always the same thing as a physical solution. Think of it this way. Every valid physical solution you find will definitely be one of your mathematical roots, but just because you've found a mathematical root doesn't mean it can be a physical solution. As we saw in our rectangular plot example, the math gave us 2 answers, but only \text-only one actually worked in the real world, $. Second, always perform a constraint check. Whenever you finish solving your quadratic equation, don't just stop there. Take a moment to look back at your variable and ask if the value satisfies the real-world constraints of the problem. For instance, if your variable represents a length, you must ensure that length is greater than 0. Finally, remember the importance of discarding roots. It is mathematically correct and logically necessary to discard any negative roots when you are dealing with physical quantities like dimensions, time, or age. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. If you follow these steps, modeling the problem, solving the equation, and then filtering your results through the lens of physical reality, you will avoid the most common pitfalls in applied mathematics. Well done today.